So this is our problem. You're adding a stream into the reactor, and it reacts either in a batch fashion or a semi-batch fashion. So we're going to start with semi-batch because that's the equations that Dr. Clausen gave us inside of the handout. We're also attempting to reproduce this graph and this graph here. So I think that it's kind of hard to start out straight with the equations that he gave us. You kind of have to think really hard about what those equations mean, and those equations don't even work whenever you try to solve the batch reaction. So with any sort of system where you're adding in mass or taking out mass, or mass is being converted, you start out with an overall mass balance. So here we've got our reactor, we've got our stream coming in, we've got our initial concentrations here. So you start with your overall mass balance, dm dt equals m dot in minus m dot out plus m generated. The total mass inside of the reactor at any given point is given by the density times the volume of the fluid that's in the reactor, and then the mass added into the reactor is given by QA times rho. You can convince yourself of this using the units. The units of QA is liters per hour. The units of rho is kilograms per liter. When you multiply those two together, you get kilograms per hour, which is the rate at which the inlet stream is flowing. So whenever you combine these two together into your mass balance, you get d rho v over dt is QA times rho. Because rho is constant, your density is not changing for your overall mass. Your components might be changing inside of the reactor, but we're assuming constant density. So it can be pulled out of the equation and canceled on both sides. And so you are left with your first of the equations on the sheet for semi-batch. So that's how this equation was obtained. The other three equations were obtained through a component mass balance here. And this is what that looks like. Now we're working in moles, so dn dt is n dot in minus n dot out plus n generated. So for one component, this whole area is my work for component A, and then B and D. Our balance around component A, you start with the amount that's inside of the reactor, Na equals the volume times the concentration, and once again you can look at the units and convince yourself that that is the equation for the amount of moles within the reactor at any given point. N dot in for A is 0 because there's no concentration of A going into the reactor. Our N generated is actually our reaction rate because the amount of A being taken out of the reactor is equal to the A that's converted. So negative RA is negative K1 times CA times CB. So when you put all of that together, we get dV CA dt equals negative K1 CA CBV, which we can't do anything else with right now because our volume is changing, so we can't pull that out. It's not a constant. So then you can do it again with component B and component D. For component B, it's a little bit more complicated because two reactions are coming in simultaneously. So we've still got the volume of B already in the reactor is equal to V times CB. Then we also have our inlet B coming in. N dot B in is equal to the flow rate times the concentration of B added. The generated term now is equal to the amount of B converted through both of the reactions. So we've got reaction 1, K1 CaCB, plus reaction 2, which is K2 CB squared, times the volume. So I just noticed, I realized there's supposed to be a V term here too, but nonetheless, N generated is now the addition of those two reactions. So our CB term, the differential equation around our CB is dV CB dt equals this whole mess. And then our concentration of D is obtained through a similar process, and you get dV CD dt equals the rate at which D is being produced. So that's how the equations are obtained. That's important to remember, that our assumption is this is through the semi-batch process. Our assumptions are going to change whenever we do the batch reactions. So we're going to have different equations whenever we use the solver on those. So before I talk about how to get these into the form we need them in, I want to talk about how ODE needs the equations to be set up. So here is a little representation of how ODE solver solves these equations. It takes a system of equations and the initial values of the components that need to be solved for, and it uses an iterative algorithm, meaning it tries something, gets an answer, checks and sees if that answer is right, and then tries another guess. And it does that over and over until it solves for dCA dt, dCB dt. And then once it gets an answer for those, it multiplies that by the time interval that it's at, and that gives it its value of CA, CB, CD. And then it uses those values that it got here. That's the output. And for the next time interval, time 2, time 3, so on and so forth, it uses those values as the new initial values. So that's an important thing to remember whenever you're solving these equations in ODE solver. Because as it stands right now, whenever it solves these equations, ODE is going to get VCB and then VCA. And whenever it tries to plug those back in as initial values, it solves it again, but it's not in the right form. It's VCB instead of CB. It's VCA instead of CA. So we need to get these into dCA dt instead of dVCA dt. And the way we're going to do that is with product rule. So let's see. This is just the 4 equations together. So product rule, if you remember, is the derivative of A times B is equal to B times the derivative of A plus A times the derivative of B. We can translate that into the equations that we're working with here. dVCA dt equals V times dCA dt plus CA times dV dt. And we know what dV dt is. We have an equation for that. We have an equation for V is a variable that we can put into our equation. C is a variable we can put in. We have an equation for dCA dt. So we can manipulate our equation to find dCA dt. So this is how it's algebraically manipulated. It's literally just algebra rearranging this. And then this is just plugging in. We know dVCA dt from our last calculations here. dV dt is just QA. So all of that is just algebra with the product rule. And then this is a lot of words, but these are just doing the exact same process for using product rule for dV CB dt and dV CD dt. So these are our three equations here. The equation for Ca dt and dCb dt, dCd dt. So putting them all together, these are the equations that are now able to be manipulated by ODE solver. So before I go in and solve those equations with ODE solver, I want to also do the algebra manipulations for batch. So here is the system for the batch reactor. Our assumptions have changed. Instead of using a flow rate of B into the reactor, we're just assuming that it's all been added at once. And because of that assumption, we have to solve for the new initial concentrations of everything, because all of that has changed. So our overall mass balance, we always start with an overall mass balance. We always follow up with a component mass balance anytime you're working with streams. Our overall mass balance is N total, the total number of moles within the reactor, is equal to the moles of A plus the moles of B. And the moles of A is equal to the A that's already in the reactor here, plus the A that's being added into the reactor. So Na in reactor plus Nb in reactor plus Nb added, because there's no A being added into the stream. So then we can calculate the Na that's in the reactor with the flow rate times, the volume of A times the concentration of A that's in the reactor already. So that is 4,000 moles. You do the same thing with B. There's B already in the reactor, concentration of B times the initial volume that's in the reactor. So there's 500 moles of B already in the reactor, and then the number of moles added is Cb added times the flow rate into the reactor times the amount of time that it was originally being added. So we've got, you can look at the units to make sure that it cancels out, but the concentration of B times the flow rate here times the time, so 0.5 moles per liter times 1,000 liters added per hour times 7 hours is 3,500. So our total number of moles in the reactor, kind of irrelevant for this problem, but it's an important thing to think about, is 8,000 total moles of everything in the reactor. Then our total volume is the initial volume here, the volume that's already in the reactor, plus the volume added here, which is the flow rate times the amount of time that the stream was added. So 7,000 liters plus 2,000 liters, 9,000 total liters in the reactor at any given, or at any point in the reaction, because the volume is now a constant. So then you have the number of moles for each component. We calculated that here. The amount of the new concentration of A initially is the number of moles of A total over the total volume, which is 0.44. Cb initially is now the same value, coincidentally. So that kind of makes sense whenever you look at the initial graphs that he gave us. You saw that the initial concentrations were about 0.44 and that they were the same. CD is 0 because nothing's been reacted yet. So that's easy to convince yourself that that's correct. So these are our new differential equations. We have to do another component mass balance. The new component mass balance, you have to remember that the volume inside of the reactor is no longer changing, so that can be pulled out of the differential equation. So and then you, inside of your volume of Cb, or the concentration of Cb changing over time, there's no longer the inlet stream of B coming in, so you don't have that term here anymore for the inlet concentration. So the rest of that is just algebra, adding the equations together. So these are your new equations that you're going to solve whenever you do the batch reactions. You no longer have the dv dt because dv dt is now 0. So now we're going to go over to MATLAB. So with any MATLAB program that I have, I always CLC clear. I always start by labeling my file. I have a header here, and a lot of people don't do something like that because they only use MATLAB once or twice, but it really comes in handy whenever you later on need to find a very specific format for something that you're working on, or just like if you don't label things correctly, it's going to be really hard to come back and see what you were doing at the time. So I think it's a really good habit to label things well. So I'm going to go to our new main file. I'm just copying over the header that I previously did. 3/13 is when I was working on this, and I'm going to put in that this was for the tutorial. So I always put things inside of functions. In MATLAB, that's not necessary, but in other programming language, that's a necessity. So I'm just going to go ahead and make our main function here. Function main example. Here we go. So another thing to remember is that at any given point, your program should be testable. You never want to continue working on any part of your program while something can't be tested, because if you make an error later on in your program and you still haven't fixed an earlier problem, then you don't know what's going wrong with your program at any given point. And that's a good way to just get completely confused and not know how to fix anything. That's where debugging gets really hard. So here, I'm just gonna give an example, like if you have concentrations, values equals ODE 45 at my file that I've already made is called ODE equations. And then tspan, why not? So whenever I try to run this, I get 50 errors because I jumped ahead and didn't think about what I was typing in. And so I can't test it. So if I kept on going without testing this and started typing things in here without testing it, then I'm just going to get confused. I won't have an answer for anything. I'll have to go back and fix this error before I can test and see if the next line of code is correct. So I'm going to start out with pseudocode, which a lot of people find annoying. Whenever I start on a problem, if I think I know where I'm going with it, then I also tend to skip the pseudocode part. But I think it's really important whenever you're starting out on a new project. So I know that in my main example function, the first thing I'm going to do is initialize my variables. Then I'm going to solve with ODE. Then I'm going to plot everything. So that's pretty much the only thing that I'm going to be doing with my main example. The only thing that I might add is that this is specifically for the Semibatch function. And then maybe later down here, I'm going to do it again with batch. So that's all I'm really doing with the main example function. So now we're going to go into the actual function where we're solving the differential equations and write pseudocode for it too. So first, I always make my header file. There we go. Oops. So there, but this time, this is specifically Semibatch. There we go. That's good enough for right now. I usually go in and add stuff later, depending on the need, but while we're working through it, I'll skip through that. And then we also need to make a function to put this into. So I'm gonna call it function dy dt equals ODE equations. And one thing you need to keep in mind, I'm going to leave that empty for just a second. Did I already? Yes. Okay. So one thing you need to keep in mind is that you need to know how ODE works in order to know what you're going to need to output. I always say you should look at the documentation for anything you work with. Documentation is required for, not required, it's usually provided for any programming language, any program that you work with, any function you work with. There's documentation for it to tell you exactly how to use it correctly. And here's the documentation for ODE 45. You can see that it needs a function, and then it needs the time span that it's running for, and then it needs the initial concentrations. It probably tells you down here how to create your function with it. Yep, right here. So it tells you that you need to put your time span here, and then it tells you to put your initials right here. So time span, initials. So before I move on, I always check and make sure that I know why things are being highlighted. So this isn't set yet. So if I tried to run this right now, it would give me an error because I don't have a return value, even though I told it that there would be a return value here. So I'm going to say dy dt equals zeros 1 1. So I know that this isn't right yet, but I just want it to be testable right now. Then these are highlighted only because they're not being used yet. So that's fine right now. Right now, our program should be perfectly runnable. If I test this, main function goes all the way to the end. If I try to test ODE equations, then it'll give me that dy dt is 0, which we expected because we already told it that it was going to be 0. So what value does dy dt actually have to be? We will work through the main function a little bit before we do that. But that's something you need to think about is like, what is going into dy dt? And that's dictated by ODE solver. So we're going to go back to our main function and start through our pseudocode. We know that our variables that we need to initialize are going to be, well, first I'll start with ODE. So if you go back to the documentation, the way you use ODE solver here, there we go. So it's going to be the time and your outputs equals ODE 45 at your function, the time span, and then your initial concentrations right there. This is the one we're using actually. So let me separate these out so we can look at them at the same time. So t comma y equals OD 45 at our function's name is OD equations, and then our time span, we'll just call it t-span for now, and then why not. So we know that our time span, we have to define that real quick because right now, yeah, these are unused, but they're also not assigned because if we were to try and run this, actually I'll just show you. If we tried to run this right now, it's going to give you an error, and that is because we don't have our t-span here. And that's why it's good to test very frequently, is because if you don't test it, then we don't know what's going wrong and we don't know what variables need to be assigned. So that's just a small error that needs to be fixed right now. So t-span, we know we're going from 0 to 7. So if we ran it again, it's going to give us an error for why not. Yeah. So our why not is going to be equal to, let's see, we're going to give initial concentrations for our differential equation here. Let me just suppress this very quickly. So we're going to give it CA, or CA naught, I suppose, CB naught, CD naught, and V naught. So now we have to define all of those things. CA naught equals, let's see, I have the paper right here. So our CA naught is 2, and I always put the units of anything that I type in just so that I can look at my code and easily tell that this is where the units were. This is why proportionally this is wrong because I gave it the wrong units here, things like that. So the units for CA naught is moles per liter of A. CB naught equals 0.25, and that's also in moles per liter. Oops. CD naught is 0. Units don't really matter for that, but I'll put it anyway. And then V naught is 2,000. Oops. Liters. Okay, and when we run this, there's an error. So this is an error we expected to get eventually. I'm going to close the documentation for this really quickly and make this a little bit easier to read. So what does this mean? A vector of length 1 was returned from the ODE equations function, but it expected to have a vector of length 4. And that's because of the way that ODE solver works. So if you look up here, ODE solver is going to take your initial values and it's going to solve the equation and get new values from that equation, and then it takes those new values and puts them into the next time span's initial values. So what we did was that we gave it 4 initial values, and then it solved those initial values, and then it outputted 1 value, and then it tried to say this new value is the new initial value here. And that doesn't work. So we're going to change our ODE equations here, and we know that it needs to have 4 now. So now whenever we run it, in theory, it should work. And it did. So that's great. It's now a testable function again. Now we can tell that it thinks that it worked correctly. That means that everything that it put in had a result, it compiled correctly. But we don't necessarily know that the answers that we're getting are correct. And we know that they aren't as of right now because we haven't even put our ODE equations in. But we're going to go ahead and put in our plotting mechanisms so that we can check and make sure that whatever values we get from the ODE solver are correct too. Because even though it thinks that they're correct now, we can't tell until we've plotted them and see what the initial concentrations are. So I'm going to grab from my previous function, because plotting is boring, I'm just gonna grab all of this. Oop. I've been putting things under the wrong headings. This will actually go here. And I'll put all of this right here. Okay, so now whenever we run this code, it should plot everything. I'm gonna unsuppress this one. Let's see where it went wrong. Now it's because I had a different naming convention in my old function, so we've got to change it so that it matches this naming convention. I like this one probably better because the concentration values thing doesn't actually make sense here. Oops. Alright, and I'm not gonna skip through some of this stuff because I want to show how long it actually takes me to code whenever I'm thinking through a problem. Let's see. So now whenever I run this, we can see that volume is at 2000. Our concentrations are all at 0 right now. And I'm also going to label the graph real quick. I'm going to steal the labels from one of my old programs. Alright. So now whenever I run it, it should show what the lines mean. There was an error. Oh, no, there wasn't. Okay. So now you can see that CD is at 0. You can't see the other ones right now, but this is volume up here. I didn't label the volume because eventually we're going to take that out. So volume is a lot bigger than all the other concentrations. So whenever you have volume, whenever you plot the volume with everything else, it's going to overshadow everything else completely. So we're just going to go ahead and take that out. So when we run it, we can see that everything stays constant now. All right. So now let's actually plot our ODE equations. Let's see. We didn't write out any pseudocode, so we're going to go ahead and do that too. So first, we're going to need to initialize our variables, define our constants. We're going to write our differential equations. And then we're going to store the answers from the differential equations into dy dt. So the variables that we need to initialize come from y naught here. T is actually unused by us. It's going to be used by ODE solver, but it's required anyway. So we're going to go to main example and look, because our y naught comes from what we defined here. I'm going to paste that over here. We're not actually using this line of code, but it's good for reference so that we can see what is inside of y naught right now. So in y naught, we've got ca naught equals y naught at 1. cb naught is y naught at 2. cd naught is equal to y naught at 3, and v is equal to y naught at 4. Now, the naming convention I used here doesn't really make sense because these aren't technically the initial concentrations. During the first iteration, what it pulls from this vector are the initial concentrations, but after that, it's using the past answers to CA and CB. So we're going to delete those knots just so that we keep this clear in our minds. Like, this is just the concentration of A at any given point. So I'll skip defining the constants for right now, just so that we can see the process behind the differential equations first. A lot of people try to jump right into writing the differential equation like this: dv ca dt equals negative k1 times ca times cb times v. And whenever I do that, we're going to get an error here called a parse error. A parse error means that what you wrote, you're setting something equal to something that doesn't make sense. So equal signs in programming don't mean the same thing as the equal signs in math. Like, for example, equal means it's checking to see if something is true. And it'll return the value true. So if I said something equals something, it's going to see if they're equivalent, and if it is, then the meaning behind the statement equals true. And a single equals actually means an assignment. So it's assigning a variable this value, but this can't be assigned anything because this is not a variable. This is an operation, a variable dvca divided by dt. And we're saying that that variable, which isn't a variable, is being assigned this value. And that doesn't make sense, so it gives you a parse error. So instead, we're going to write it in a way that makes sense to MATLAB. This equation is actually wrong, so we'll just delete the whole thing. We're going to say dca dt equals, and now because we're assigning a full variable something and not an operation something, it shouldn't give us an error whenever we type the right hand side. Now it just says that it's unused, which is not really an error, that's a warning. So now we're going to write our differential equations, the equations that we solved earlier, 1 over v. And something that you can remember is that there is a built-in order of operations to MATLAB, but all of my coding professors have always said, like, it's better to just use parentheses and not memorize the order of operations, because it's more readable if you use parentheses. If you overuse the parentheses, then it's obviously harder to read in the first place. But most of the time, for debugging's sake, it's good practice to just make your code as readable as possible. If you type something and you're like, that doesn't make sense, or this is really hard to understand coming back to it, then it's a failure on your part. You need to change that line of code, and that's something that is just good programming practice in general. So 1 over v times negative k1 times ca times cb times v minus, qa times cd. So now here's where you evaluate, is this going to run? We've already tested it before we put this line in. And if you try to run this now, you're going to get an error. When you go up here, always when you're debugging, start from the very top of the errors, because usually the errors that follow are due to one of the very first errors. So you got error in ODE equations. It's your K1, because you used a K1 but never told it what K1 is, and that's because we never initialized our variables. So we're going to go ahead and put all the variables we need. K1 equals, 0.5, and that is in liters per mole hour. And then we also used QA equals 1,000 liters per hour. And then that's all that we used in this equation. So now it should be testable. Yep. Awesome. So now we're going to write the rest of our equations. dCB dt. And what you call these doesn't really matter. We just need to assign it to a variable, and then we need to be able to store it into our output. So dCB dt equals 1 over v times k2 times cb squared times v. And even though I know that it's not going to say to the power of 2 times v, I'm going to put the parentheses around this anyway, just because it's good practice. It makes, not this one, it makes our code much easier to read whenever I know this is the only thing that's being squared right now. Let's see. Oh, I'm reading the wrong equation. This one is actually for CD dt. V times V minus QA times CD. So right here, I've misordered it, which is fine whenever, as long as we know where to store it into dy dt. So if I were to continue and do dCB dt equals, that's totally fine. We're allowed to do that. But just to make things easier on myself later on, I'm going to write the equations in the order that I'm going to store it. And that's another thing with good programming practice. Always just make things very readable for yourself and anybody else who looks at your code. Times CBA minus CACB. And another thing I do is I know that these are each terms of an equation. So whenever I multiply things together and then subtract them, I always put spaces in between them just because it's easier to read for me. That's a convention a lot of people follow too. Times 2 times k2 cb squared times b minus times cb. Okay. And then our last equation is dv dt equals qa. So those are all of our equations that are going to be solved simultaneously. I kind of went through without testing a lot of them. So now we're going to go back to our main example and test them. So any errors that come now, we know were during the typing of this area. So that's why you want to test frequently. It's really easy to figure out where your errors are from. This time it's because of CBA. CBA here is not defined, so we're going to go back up here and define CBA. And that's our added concentration of B, which is 0.5 moles per liter. And, oops. Okay, so now when we run this, it should work. In theory, K2, we also did not define K2, equals and just per mole hour. Now it should work. And you'll notice here that the concentrations are still constant. And if you look back at our code, it's because we calculated all of these things, but we didn't do anything with them. So we want to return these values because ODE is going to use them to solve for every iteration. So we're going to store them into our output matrix, dt at 1, 1 equals dCA dt. And like I said before, we have to store these in the order that it pulls those values out of the why not. So we have to put A first and then B, D, V. So down here, dy dt at 2, 1 equals dCB dt, dy dt at 3, 1 dy dt at 4, 1. And another thing to note is that we're not going to use this volume. We don't need it in our graphs up here whenever we run it, but we're going to put it anyway because it has to use those volumes that it calculates in every single iteration. So now the only thing is cleaning up our code. I noticed that I put these concentrations or these variables under the initialized variables and not under the constants. And then just do anything that might make your code easier to read. You have less to clean up at the end if you do it along the way though. So now when we run our code, dCB dt, and that's because we never changed this one to match our right. And there is something wrong with this. So the way to troubleshoot something like this is to look at where the concentrations are starting. Let's see, look back at our original code here. It's supposed to start at 2 and 3 and 0. So, and then the ending concentration for this one is 1.4 on our original. It's supposed to be much lower. So that means that probably something we wrote in our differential equations was incorrect. So we'll look back at our differential equations and make sure those are correct. Negative K1 CACB V negative CA times QA. And that is where we went wrong, is because this is supposed to be CA times QA. QA times CBA. And that's what's called a silent error. Those are the most difficult ones to troubleshoot in your code, is whenever there's something mathematically wrong. And that's why you need to be able to do the math behind these calculations as well as using MATLAB, because MATLAB is just a tool for you to use to solve the equations. It's not supposed to know how to do the actual calculus and how to do the actual chemical engineering behind all of this. So 2 times K2 times CB squared. That all looks right to me, so we'll go ahead and test it now and see if that fixed it. And it looks like it did, but hold on is still here. So the way to make it get rid of the previous ones is by saying hold off. There we go. And that is how you graph your semi-batch equations. You do the exact same thing for the batch ones too, and I'll just show you my code for that one right here. Oh, for the batch ones, I mean. So for the batch ones, it's the exact same process. You still initialize your variables, except that now they're different. Your constants here are the same, but your new volume is different. You don't have a differential in volume, you have a constant volume here. You only have 3 differential equations. I go ahead and store the volume every time, just because that's something that I did while I was testing and I never took it out. And whenever I look at my code here, going back, I can tell this is extraneous. I didn't need to graph, or I didn't need to output this too, but I did it because I used it for testing. So if I run my original equations here, here's my original code whenever I did this assignment. I can get rid of this so that we can just look at this graph. And whenever I run this one, you can see the graph that I got, which is different from the graph that Dr. Clausen gave us, but we agreed that this is probably the right answer here.